Alright, today we're going to cover heat and gases. There's a lot to do, so you'll want to pause it at different points and make sure you've done the quiz beforehand. Let's start off with some equations. We've got three key ones. First one, we need to talk about pressure. Now pressure depends on how much force I exert, so how much I'm pushing, how much I weigh, whatever that force might be, and the area over which. Let's look at a tank. It's a measure of the force exerted per unit area. Okay? The tank is designed, of course, to have a very big area. And that means that the force is spread out over a much bigger area, which decreases the pressure, makes it very small. And that means that instead of sinking into the ground, I can go on top of it. Now remember, the force stays the same. It doesn't make any difference whether I have a big tread or whether I have a very thin tread. But the pressure it exerts, so it's spreading the same force over a bigger area. We can explain this in terms of the equation. Pressure is force over area, or I could rearrange it. Units of force, you need to remember this, is newtons. Units of pressure is newtons per metre squared, or pascals, PA, named after a famous scientist. Okay? These are key things. We'll come back to these throughout. Let's look at density now. Density, now a lot of people put little d for this, which is wrong. It's a Greek letter rho. And it's a measure of how much m for mass in a given v for volume. So it's my mass per unit volume. It's the mass I would have if I had a metre cubed of that material. And if I rearranged it, remember mass has got to be in kilograms, volumes in metre cubed. If I had grams over metre cubed, units of this would be grams per metre cubed. If I had grams per centimetre cubed, I'd get grams per centimetre cubed. Think about what your units are. Last one. If I have water like this, can you see that the water's coming out just a trickle here, but it's already gushing out the bottom? And that's because the pressure goes up as you go down. You know that because your ears hurt as you go further underwater. But we need an equation to say how much does it go up. Well, we got this equation. The pressure difference between the top and the bottom, so let's say if we're here, would be G, on Earth that's 10, times the depth. So if I was looking between the top and this bottom one here, that would be my depth, times the density. That's the density of the thing, the fluid, that's pushing down on you. So, pull of gravity G, depth, and density. These are three things. I think of this as P equals G D rho. G D rho. You want to write that down. Always remember it. Alright, we're now going to be applying those three to different situations, and gases are very important. Very important one. How does a fluid, remember that could be a gas or a liquid, how does it exert a pressure? Well, look at those molecules. We can't see those in real life because they're so small. This is just a model. But what are they doing? Now, some people say it's when they collide with each other. Well, they are colliding with each other, but that isn't when they exert a pressure. They exert a pressure when they hit the walls. I don't like the word hit. I'm going to say they collide. So I'm moving already, randomly, or in Brownian motion. They collide with the wall, much better than hit. And when they collide, we'll think about it, they're going to exert a force. Okay? Because I've got force and they ask me about pressure, what equation relates them? Which one of those three? Well, pressure is force over area. Okay? They're my 4 marking points. Make sure you've got all 4 in your answer. There's a very important temperature scale, and you're used to using things in degrees Celsius, but that isn't a very good temperature scale. It's based on 0 for freezing and 100 for boiling water. We now want to use Kelvin, also called the absolute temperature scale. And we need to be able to convert them. Now, minus 273 degrees Celsius is 0 Kelvin, also known as absolute zero. Now, that's the point where you've got zero kinetic energy. Let's see if we can convert these 4. Well, 330, 237, the 1.15 is there because that's a slight correction to this. Don't worry if you've missed that 0.15, that's been pernickety. And the last one, 100 Kelvin, so make sure you can do those conversions. So, which one are we always going to talk about in physics? We're going to talk about the Kelvin, the absolute temperature. Another name is the absolute, and if we want to convert between the two, if I had Kelvin, I'd subtract 273, and if I had degrees Celsius, I'm going to add 273. Whenever we see temperature, for these gas laws, we're going to use the absolute temperature. Now this is how I think about the 4 properties of gases. There's 4 things that will affect your gas. They are pressure, absolute temperature, volume, and the number of molecules. And they're related in different ways. We need to know how to relate 2 of them together. Okay? Now if we keep these 2 if we're going to change these two, look at how they affect each other, we want to keep these constant. And they ask you for assumptions. So let's look at this. So, pressure, volume, absolute temperature, number of molecules. Which one do we want to relate? Let's relate these two. Boyle's law says that if I increase the pressure, then the volume goes down. Or if I increase the volume, the pressure goes down. P1, V1, the pressure at some time times the volume at that time equals the pressure at another time, maybe when I've squashed it or expanded it, times the volume at that time. Okay? If I know three of these, I can use this equation to find the other. And they might ask you about some assumptions. So what assumptions have I made? Well, if this is true, like I said, these two must be constant. So your assumption is that absolute temperature is constant and the number of molecules are constant. What about these two? If we're relating pressure and temperature, we call that the pressure law. P1 over T1 equals P2 over T2. If I increase the pressure, the temperature goes up. If I increase the temperature, the pressure goes up. Okay? It's the opposite way around for this one, which is why we have the divide instead of the time. Now, what are the assumptions with this one? Well, I'm changing these two, so the volume must be constant and the number of molecules must be constant. Okay? They're my laws, think of your assumptions. Let's do one more. So describe and explain what happens to the temperature if the pressure is increased, or it could be the other way around. Tell me what happens to the pressure if I increase the temperature. Now, what am I going to say? First of all, tell me what happens. As the pressure increases, the temperature goes up. The next thing, because I know from that law the pressure is proportional to temperature, that's what that law tells me. If I double pressure, I double temperature. I could state that law, that's the same thing. I could do these interchangeably. Now, this is very important. When you've got any question with temperature in it, tell me what temperature is. Temperature is a measure of average kinetic energy. That's a really important learning point. We can put that in our answer, it makes it clearer. Particles have more kinetic energy on average because the temperature is going up. So therefore, what are they going to do? Well, they're going to be moving faster. So there's going to be more collisions between them and the container per second, or more frequent collisions. Don't just say more collisions, that's a bit vague. And there's more force per collision. So they're flying around, they're going to be gliding dum 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 dum, and there's going to be more force on average per collision because they're moving faster. Make sure you've got all those points. And I could relate force to pressure by my equation as well. Notice how I'm putting my equations into my answer, very important. Let's look at an example. I've got a pressure, let's call that P1, and a temperature at that time, let's call that T1. Now notice this is in Kelvin, so we're all good there, we don't have to convert it. What will the pressure be if I change the temperature? Let's call this T2. Well, I've got a pressure and two temperatures, so I'm going to state pressure law, plug in what you know. I could rearrange it first, or I could plug my numbers in there and rearrange it. It's up to you, whatever you find easiest. Put my numbers in, get your answer. The units of pressure that I get out will be the units I put in, so it's pascals. Should be quite easy. What assumptions do I make? Well, remember, think of my four things. I've got to say that the volume's constant, the number of molecules is constant. I know gases escaped. One more. Diver, he's got a bit of a jippy tummy. He lets one go quite far down, and the pressure is 4 times the atmospheric, so he's gone quite deep. Now, as he goes up, a bubble's going to go up, and what's going to happen to the pressure goes down, it should go up. So that means that the thing's going to expand. So how would I do this? Well, the best way of doing it is saying Boyle's law, and I could rearrange it, and I could say that this volume, if I think about the pressure's 4 times bigger, so I've got 4 times the volume as I go up. Okay? That's it. We've looked at our 3 formulas, we've looked at the absolute temperature scale, the Kelvin scale, we've looked at these 2, and we've applied them. Do the quizzes, make sure you've got it, go back and pause it if you need to. Good luck.